Hey guys, Julia, welcome back to Hardware 3D. Today's topic is full screen filters. Stuff like applying a blur filter to the output of your rendering pipeline. Now this is going to be an interesting topic. It requires some theory, but before we jump into that, I want to talk about our outline effect and some problems that we have with it, because that is going to lead us nicely into the topic of full screen filters. So if we look back at our familiar Sponza test scene here, we can see, we got our outline effect here looking real nice. We can set the color of the outline. We can change the size of the outline. It's all good. But now let's look at it not for one of these boxes, but rather for something else. And if we turn on the outline, we see, okay, it's a little funky, a little bit funky, but still sort of maybe passes. Not really. Scale it up, and yeah, that's some real bullshit right there. What's the problem? Well, you're scaling, the way it works, you should be familiar with this, but you're scaling up the model, and drawing it again, right? Well, scaling is basically moving it away from the origin, moving all the vertices away from the origin. If the origin isn't in the center of the mesh and you scale the vertices, you're going up here, right? That's not good. And you might say, well, Chili, just make all of your meshes have their origin at their center. Well, that still doesn't fix all the problems. Take a look at this this torus here, also known as a donut. And let's scale this boy up, okay? The outside is going to look something like this. The inside is going to look something like this. So if you apply your effect, you're going to get a nice outline here, but the inside is not going to be outlined. That's not good. Now, one way you could try to solve this is, instead of scaling all the vertices, you could offset them in the direction of their face normal, in that direction, and then you'd get nice outline on the inside and the outside. So the simple scaling effect doesn't work nice for convex objects, but this offset effect can work nice for convex objects. And if you remember the previous tutorial, we actually implemented that, although I sort of glossed over it. But you can see here the offset vertex shader. You multiply the normal, the face normal, by some offset, just some constant value, and then you add that to the position to get the new offset vertex position, and then you can draw again and get your outline from that. So here we see we've selected the lion, whatever this thing is, in the Sponza scene with our new technique, and the outline looks pretty good, doesn't it? If we increase or decrease the offset, we see it is not flying out. Let's try this with our good old friend Sponza 11. It's looking not too bad. Maybe a little funky, but it's looking better than it was before. So let's turn up the juice, shall we? Here we go. Whee! Oh, it is coming apart at the seams. Okay, so here's the problem with the offset outline effect. It works great when your mesh is continuous, all your vertices are connected to each other, triangles share vertices. But if you have a mesh with sharp corners, so you have triangles that are connected but don't share vertices, and then when you offset those, you get like this, which isn't good. Another problem that is pretty easy to predict is thin geometry. Even though they're two-sided, it's going to offset only in one of the directions. And also, take note that it's not going to respect things like alpha channel. Now, the solution to this is very simple. Instead of working in geometrical space, we're going to work in screen space, on the pixels, with no inkling of the geometry and the distances behind all this stuff. So if we render, some geometry to the screen, we've got those pixels here, and then we want to create an outline of this. We just need an algorithm that can basically do something like just set all the pixels that are close to the ones that are already set. So for example, anything, within 5 pixels, set that. And then we'd have our outline, and it wouldn't be dependent on any kind of geometry. We'd also have the same width of outline independent of how far away the object actually is. It's just a true outline of the pixels as rendered. And it'll also allow us to do some cool things, like instead of just a solid outline, you could have an outline that fades out, kind of like a halo effect. Now, in order to do the specific technique that I have in mind, we're going to need a full screen blur filter, kind of like a Photoshop filter. Now this video is only going to tackle how to do full screen filters, and we'll actually implement the outline effect in the next video. But before we dive into the API code required to do full screen effects, let's take a step back and look at some of the theory of filtering and signal processing in general. Now, many of the most common and useful filters that you're going to work with work on a principle called convolution. Sounds kind of scary. You may have heard of it before, especially recently in deep learning applications, convolutional neural networks, making big splashes. But although it sounds scary and complicated, it's actually pretty intuitive if you look at it from the right perspective. So to start off, we're going to look at the case of one-dimensional convolution of just two signals, basically just two functions. So I got this Java applet. I figured out how to play Java applets even though no browsers support them anymore. And so, what do we got here? Well, we got a signal. Pretend it's an audio signal. It could be anything though. This is our input. And then here we have our filter, which is another signal. It's usually a much smaller signal, and we call that the kernel. So you've got the input signal and you've got the kernel. And you're going to do a convolution between the kernel and the input to give you an output. So what is a convolution? Well, first let's get our two signals. So let's say the kernel and the input, they're going to be the same. They're just this very simple square wave. All right. Now what a convolution is you basically slide the kernel across your input signal like this. And it builds up, as you slide it, it builds up this output signal. Now the way it works is actually very simple. All you do is for every position of sliding this kernel, so let's start at this position here, you multiply the kernel times the input signal. So if we multiply these two together, we see that, well, the zeros, they cancel out those parts. So the blue signal here is 0 here, so that quelches the red part here. The only place that gets through is where they're both not 0, and that's here. Then you take the area under this curve, this area, and that is your output signal. So we start here. There is no overlap, so the area is 0, so the output is 0. But as you get into here, there's a little bit of overlap, so your output goes up by a little bit. Then as you slide this way, there's more overlap, so the output value becomes higher. More and more and more and more. Here you reach your maximum. They're completely overlapped. And now it's going to get smaller and smaller and smaller. And that's all there is to convolution. You multiply the two signals by each other. You take the area under the curve. Now you might be wondering, okay, that's cool, but how does it help us? How is this useful? Well, the shape of this kernel will determine different filters that will be applied to your input signal. So this kind of square wave function kernel here, this is actually a low pass filter. It cuts out high frequencies. So if you look at our signal here, it's got a very big jump and a very big jump down here, discontinuity basically, which is a high frequency component, very sharp jump. And when we apply our kernel to that, we turn that jump into a smooth ramping up and ramping down. We lose the discontinuity. So you see here, we're actually applying a high pass filter. One other thing you'll notice is that the signal here only reaches this point, but after we apply our filter, we've spread it out. That's another effect of this low pass filter. It spreads out the signal a little bit. All right, now we're going to change our input signal. Instead of it being a square wave, it is going to be a triangle. So now when we slide our square over this triangle, what do we get as our output? Well, it's smoothed it out, right? So now, instead of having that sharp change in our slope, we now get a gradual change in slope. So you see that this function here applies a smoothing to the input signal. It takes a discontinuity, it turns it into a ramp. It takes a ramp, and it turns it into a smoother curve. All right, let's take a look at another one here. You know, I said this was a low pass filter. Let's put it to the test. Here's a signal. It's basically got two frequencies on top of each other. A very high frequency signal here, and then a low frequency signal like this. And when we run our kernel over that and we look at the output, we see that basically the low frequency part was more or less maintained, but the high frequency components were all removed. If I make it even narrower still, I should be able to get more high frequency in there. Yeah, you can start to see the high frequency wiggles appearing in this signal here. The narrower you make this, the more the high frequency will get passed through. The wider you make it, the more they're going to cut out the high frequencies. Now let me show you one more effect of this low pass filter. I'm going to center it at 0 instead of having it start at 0. And what's going to happen is when we do this convolution here, these spikes here, they basically bleed out in these directions, which is exactly what you would get if you applied a blur filter. If you apply a blur, the outline of the blurred object is going to bleed outwards according to the blur radius. So you see a blur is just a kind of like a low pass filter, what we've got here. So what we want to do is basically do this, but in 2 dimensions for an image. So for the 1-dimensional case of convolution, you have your kernel signal, small kernel signal, and then you have your input signal. You slide your kernel along the input. At every point of that sliding, you multiply them together and you take the area under the resulting curve on the right-hand side. Well, it's the same idea for 2-dimensional convolution of an image, basically. So you have your kernel, your filter kernel, which is a small 2-dimensional grid of pixels. Then you have your input, which is a much larger 2-dimensional grid of pixels. You slide the kernel along the input image, and at every point of that sliding, you multiply these values by the values in the image, you add them all together, and that's your output. So here we can see where the output pixel is on this side, and on this side we can see where the 9 input pixels are. And as I slide this along here, I'm sliding my kernel along the image, and it takes all those pixel values in, multiplies them by the factors in the kernel, and it outputs the single output pixel for that position. And so we can see here, when we have all of our inputs on dark pixels, the output is also going to be a dark color. But when some of the inputs are on light pixels, the output is going to be a lighter color, because it's basically just more or less an averaging of them. Notice that at the very edge of the image, it's all black here, because there's a trick, something to think about. When you're on the very edge of the image, you don't have your full set of input pixels, right? So what do you do for those question marks? And what the person here has opted to do is just don't output those pixels. Only output pixels for which you have a full set of inputs. We'll talk about that in the next video, I think. So let's implement our very basic box filter here. You can put in the coefficients for your kernel. All those values of the kernel that will be multiplied by the input image. So what I'm going to do, here I'm going to fill it with all ones. This is basically equivalent to that box filter that we had in the 1-dimensional case. And you can see here, okay, that's a bit of a problem, right? It's very bright. Why? Well, because you're basically, for every output pixel, you're adding together 9 input pixels. So it's going to be on average 9 times brighter than what it was originally. So if we want to take the average, since we're adding 9 things together, we should also divide by 9. And if we do that, this is what we get. So this is our very simple box filter blurring the image. Here, if I take the image back to identity, we'll see, yeah, it's sharper. So the box filter does blur it. So to recap, what we need to do is first render our scene to some surface, some texture. That's going to be our input. Then we're going to render another image. And what we're going to do is basically, for every pixel in this image, let's say for this pixel here, we're going to look at that pixel in the input image. We're going to look at all of its surrounding pixels, do some operation, multiplying them all by some values, adding them all together, and the result of that is then going to go in here. And we do that for all the pixels in this output image. We look at the input, we look at all the neighboring pixels, and we use that to determine what color is going to go into here. So for this, we're going to need a little bit of new technology in how we deal with the API. Up until now, we've only been rendering to the swap chain. What we actually need to do is render to some other surface outside the swap chain and then use that as the input to render to the swap chain. So this we will call our off-screen surface. Initially, we render to the off-screen, and then we use the off-screen as an input to render to our swap chain. Now, up until this point, we've only been binding the swap chain as the render target. But now, we're going to have different things that we want to bind as render targets. So I want to create a class to encapsulate the idea of a render target. So if you look at the commits here, we see the first commit in this new section is render target and depth stencil. So we've got a class, render target. It's going to encapsulate the idea of a render target. So it's going to have a view on a texture and a target view. So it's going to have two views on a buffer resource. It's going to have a view as a texture and a view as a target. Basically a view as an input and as an output. And you got some functions here. You can bind this render target as a texture, or you can bind it as a target. Now, there are two bind as target functions because when you bind the render target, you have to bind the depth stencil at the same time. So I've got one overload here that only binds the render target, no depth stencil. So you're not allowed to use depth or stencil buffering. But here, there's one that will take a depth stencil along with it, and that will allow you to bind them both at the same time. Which of course brings us to the other main class that we've created here, the depth stencil. You can bind just the depth stencil. There's also a function to clear the depth stencil. Note that much of this functionality is going to change in the future. This is just a basic start on the idea. So if we look at renderTarget.cpp, we can see its constructor is very simple. It just creates a texture resource. You've seen this before. And then creates a view on it as an input, as a texture. And then we create another view on it as a target. I don't think we've actually gone over creating renderTargetView descriptor yet, but it's very simple. You set the format, and we're just going to set it to the same format that is used to create the original resource, which for our case is always going to be BGRA8. The second parameter here tells the dimensionality of the render target, which for our case is always going to be, texture 2D. And then the third parameter here is actually a union. So which union member will be active or will be assumed depends on the setting here. So we said texture 2D. So now we initialize it with D through D11, text 2D RTV. And what this thing is telling it is it's telling it basically which MIP level to render to. And we want it to render to 0, which is the only MIP level that we have in here. There you have it. There's the creation of our off-screen render target. And then the other stuff should be, straightforward. You should understand it from previous videos. If you want to bind it as a texture, you set pixel shader, set shader resource, and you use the texture view. If you want to bind it as a target, output merger, set render target, and you use the target view. Otherwise, there's nothing amazing in here. It's the same with depth stencil, right? I mean, the creation here, we've already created a depth stencil buffer early on in the series, and we've bound it. Here's a clear function for you too. Beautiful. Now, one thing you might notice here is these guys both inherit from something called graphics resource. Something I created, and the reason I created it was because originally, these functions here, these helpers that allow access to stuff in graphics, get context, get device, get info manager, they were originally in bindable. So if you wanted them, you had to inherit from bindable. But I don't want render target and depth stencil to inherit from bindable. I find them as a different concept than the bindables that you package together in a drawable. So it doesn't make sense to use inherit from bindable in order to gain these functions. So I pulled it out into its own class, graphics resource. And then bindable inherits from graphics resource now, and so does render target and depth stencil. And that allows it to do things like graphics throw info, infoman, etc., etc. Now in graphics.h, because we now have the ability to bind off-screen surfaces for rendering, we also need the ability to bind back the swap buffer. So I added two functions here to be able to bind the swap buffer. To bind the swap buffer alone and to bind it with a depth stencil. And there's no surprises here. I also added functions to get the width and height of the swap chain. And I removed the creation code here for creating a depth stencil because now that is going to be outside of graphics. The person using graphics will be able to create and manage their own depth stencil buffers. It won't be hard-coded into this class itself. So then if we look at framecommander.h, we add the depth stencil. And we construct it here, and then every frame we clear the depth stencil, and we bind the swap buffer with the depth stencil. That's it basically. We just got these two classes here, render target and depth stencil, that are going to allow us to manage these off-screen surfaces more flexibly. All right, so now let's use this off-screen surface tech we've developed and do a little filtering. We're going to do a very simple filtering. We're going to do a negative effect. So a negative is basically you take the complement of all the channels in the image. So for example, black would become white. White would become black. Red would become cyan, etc., etc. So the actual process of this is very simple. All we do is we take in the input color and we do 1 minus that color for every channel. Now the only question is, how do we achieve this process that I described earlier? The process of, for every pixel in the output, reading from the off-screen surface. The answer is we create some geometry. We create a single quad, which is 2 triangles, and geometrically, those triangles should exactly fill the area of the screen. And then we map the corners of these triangles exactly to the corners of our off-screen surface as a texture, so that when we're drawing this point on the screen, that corresponds to that point on the triangle, which will correspond to this point on our off-screen texture. So what we're doing here is in the frame commander, what have we got here? So we set up some full screen geometry. We set up a vertex layout. The only thing it has is 2D position. And those positions are just -1 to +1 coordinates forming a quad. So we can see that these are normalized device coordinates. So our geometry is going to directly store normalized device coordinates, only 2-dimensional because the Z isn't required. Indices are for the quad, so 0, 1, 2, 1, 3, 2. We're going to register those vertices and indices in our codex. And I use a $sign here just to denote a kind of like a global. So all full screen filters, they require this kind of geometry. So we don't have to repeat it. We can just have one global one that is always going to be resolved out of the codex. And then the most important part is the shaders that are going to be using that full screen geometry do something interesting. So let's look at the full screen vertex shader. So it takes in a 2D position, and it just says the output position is going to be what was input, but add a 0 for the Z coordinate and a 1 for the W. So this will ensure that no perspective divide happens, and otherwise it's just passed right through because we're already in NDC space when we receive these coordinates. And then we have to map the UV coordinate. So we can see that these NDC coordinates map to coordinates in texture space. This one would be 0, 0. This one would be 1, 1, etc., etc. And this just performs that mapping, right? For the X, you add 1, divide by 2. For the Y, you subtract 1, you negate that, you divide by 2, and you come at the right answer. It's a very simple linear mapping. So now we have our UV coordinates set up to read in from the off-screen surface. And all we do for this very simple pixel shader is for every UV coordinate in, we read that coordinate in from the off-screen surface, get the color, and we get the complement of that color. So here in the frame commander, after we've created that geometry, down here, well, here you can see we've created an off-screen render target that gets initialized here. And what we're going to do is first we bind the off-screen render target. We do our normal rendering to that render target. And then afterwards, we bind the swap buffer. We bind our render target as a texture for input. And then we're going to bind, the vertex buffer, the index buffer for the full screen rendering, the shaders, the layout, and then we simply draw indexed using the number of indexes in our index buffer. That's going to execute these shaders, and we're going to get our negative. And here's what that looks like, and I'm sure you can agree it is quite a funky monkey. As you might expect, the places that are dark have become very light, and the places around the light here are actually darker. So if I move this light down, you can see this spot here on the ground gets very dark because it's obviously being very light, and we're taking the negative. All right, now let's do a little more complicated effect. Let's try the blur effect, actually. Simple box filter. So with the previous effect, we were just reading a single pixel and then performing some operation, outputting it. But now with a blur effect, we have to read neighboring pixels, perform some operation on all of them to come at a single output pixel value, a single color. The operation is going to be simply add them all up and then divide by some number. Now we can use the exact same full screen vertex shader will work for basically any of our full screen functions here. So all we need to do is change the pixel shader. Now here is where things get a little interesting. So we've got to loop over a square section of pixels. The question is, how do we get, for example, let's say this pixel here that we're working with is, I don't know, 50-50, assuming, 0, 0, top left. And we want to get at 50, 51, the pixel below it. How do we do that? Just think about it. The problem is the input to our pixel shader, we don't know really what pixel we have here. The only input we get is the UV, which are values between 0 and 1. They're floating point values. So the pixel below this one, let's for argument's sake say that the V of this one is equal to 0.1. So the V of one pixel below, what is that? Is that like 0.11 or 0.104? It's hard to tell, right? Well, not really. We just need to use a little math. So if we know the height of our image in pixels, which is the same as the vertical resolution of our output, so let's say that is 720. Then we know that the distance between pixels is going to be 1 divided by 720. So if we want the pixel below our current pixel, we just have to add to our current pixel's V 1 over 720. And you can see that's what I'm doing here. First, I get the dimensions of the texture. I get the width and the height. Then I create something called dx and dy, which is the distance in x between neighboring pixels and the distance in y between neighboring pixels, which is just 1 divided by the width and the height. Now what I've got here is a loop. It's looping from negative r to positive r in the y and in the x, where r is equal to the radius of our blur function, our kernel. So you can imagine x, y to be offsets from the position of the pixel, the output pixel in question. So if right now we're working on outputting this pixel here, xy equals 0 represents this pixel on the input, the exact corresponding pixel. And we're looping through -3 to +3. So we're looping through this area here. So x and y are the offset in pixels from the current output pixel position. But we don't want the offset in pixels. We want the offset in texture coordinate space. So what we do is we multiply x and y by dx and dy. And that gives us the offset in texture coordinate space. We add that offset to the base position, and that gives us our texture coordinate reading position in this loop, which is looping over all the pixels under the space of the kernel. And then for each of those pixels that we're reading from the input, each of the pixels in this square space here, we're just going to add their value together in an accumulator here, a float 4. So we sample the input texture at that texture coordinate. This is the off-screen surface, remember. And then at the end, we need to divide by the total number of pixels added together, because remember, we want to take the average. So if we're adding together 9 pixels, then we got to divide by 9 at the end. Now you can see in here, you probably noticed that there's a mistake in the math here. And if we run it, we see that the image has definitely become blurred, but it's also brighter than we're used to. So the problem, if you haven't already figured it out, well, this R here, this isn't the width of the kernel, this is the radius. So it extends from -3 to +3. That's -3, -2, -1, 0, 1, 2, 3. The width of the kernel and the height of the kernel are 7, not 3. So it should be 7 times 7. This should be 49. So what I do to fix that is, instead of just hard coding it in here, I add another const which figures out the divisor given the radius. And that's just using this simple formula here. And now we see our familiar scene, but yeah, things are looking a little myopic. They're all blurry, which is what you'd expect. Good stuff. So our blurring filter is working. Simple box filter for blurring. Now before people all race each other to the comments trying to tell me how I'm doing it wrong, I realize this is not the most efficient way to, approach this problem, and I will be showing you in the next video. I'll show you a few improvements, but not all the improvements you can do. Mainly, my goal here in this video and the next video is to just teach you the basic concept and the theory behind it and how to implement it in Direct 3D, not all the little min-maxing optimizations you can do. We may look at that in the future sometime if it becomes pertinent, but that's not my goal here today. So I know, the calling get dimensions here is not the fastest. There's faster ways of doing this. This loop could be improved. The way you sample the texture, there's optimizations you can do there, and there's a big algorithmic optimization called separated filter, which we will actually be looking at in the next video. That's gonna about do it for this video. In the next one, we're gonna take this blur technique and we're gonna use it to create our improved outline technique. And I'm also gonna show you a little bit of optimization for how you can optimize these full screen filters by separating them into vertical and horizontal passes. But until then, thanks for watching. Hope you enjoyed this video. If you did, please, the like button helps a lot. And I will see you soon with some more Hardware 3D.